You're listening to The Digital Factory, presented by Formlabs. I'm John Bruner.
And I'm David Cranor.
In this series, we're going to be exploring digital manufacturing in conversations with experts who are changing the way things are made and shaping the future of the factory floor. We're speaking with the founder and CEO of Desktop Metal, Ric Fulop. Ric, good to have you on.
Hi there.
Desktop Metal has recently announced a couple of products, and they were very exciting. There was a lot of interest when they came out. Essentially a new category of 3D printer. I wonder if you could explain what it is that Desktop Metal has produced or is producing.
Yeah, so we are making two new products. They are both aimed at metal printing. And the goal of the company when we started it was to basically make metal more accessible to people that want to do prototyping and lower cost to people that want to do mass production. I think that today you have people that print metal parts, but they're really inaccessible. Only Fortune 500 companies might have a machine. And, it's relatively a small market. It's only about $1 billion worth of metal machines. They're all, average machine installed is about $1 million. And compare that to CNC machining, the equipment for that is about $80 billion a year, or, industries like powder metallurgy, which is about $260 billion a year, and all metal parts is about $1 trillion a year, and they're roughly in the 10 largest countries combined. So printing of metal parts is still in its infancy, and it's a very, very small market compared to metal parts as a whole. We felt like the reason why it's a small market is because the technology is not accessible, and it's too hard to use, and it's too expensive for use in production. And so as a result, the only people that make parts that are 3D printed with metal today are industries like aerospace, where they're able to pay very high price, or industries like implantables in medical, et cetera. So what our two machines offer is, number one, it's the first system that can print metal parts in an office environment.
This is because it doesn't require elaborate ventilation, or?
No, it has more to do with the fact that we changed the process so that it would be safe, so you could handle the materials in an office environment. And we also changed the process so that it would be a lot less expensive. So in average, our office system is for the same build envelope. It's about a tenth the cost of laser powder bed fusion, which is a technology it replaces.
Can you tell us kind of roughly what the existing metal 3D printing processes, how those work, and what makes them hard as well as expensive, and then what your particular take on the process is?
So the existing technology to do metal 3D printing is something called powder bed fusion. You take a bed of powder and you spread a very, very thin layer, as thin as a human hair, and then you hit that with a laser and you melt that layer. You scan that laser, and then you put another layer of powder and you melt it, and you continually do that until you have a part. The process is very expensive and very slow, and these metal powders are pyrophoric, meaning they're explosive and they're hazardous to your health if they get out. So you basically need to maintain them and manage them in a controlled environment. In many cases, if you're printing things like titanium or other materials, you need special rooms that are explosion proof, and so that's kept the technology from really becoming more accessible.
The dust and the explosions.
Well, it's not so much the dust of the explosion. The printers don't generate dust or explosions, but the fact that they had to put all these claptraps on the machines so they don't generate dust or explosions is what makes the systems expensive. They're in average $500,000 just for the printer, and then you add all this other crap. You end up with a machine that's fully installed and turnkey, approaching $1 million, and you need dedicated operators, people that literally do nothing but run the machines, and so you end up with a very expensive proposition, and they're slow, so you wouldn't use them to make everyday metal parts.
So your printer does not use the dust?
Our printer uses a media that looks like a crayon. So we bound all the metal powder in a polymer matrix of a variety of polymers, and then that is extrudable. So it works the same as an FDM printer. You can make metal parts, and then we have a second process where we have a microwave-enhanced sintering system that will sinter the parts into a fully dense metal object. Those two parts give you our studio system, which is in reality the first office-friendly metal printer in the market.
Wow.
It's going to revolutionize engineering. People will be able to rapid prototype parts out of a variety of alloys that they literally couldn't use before, and that's actually pretty exciting.
It sounds like there are several fundamental advancements that you guys have made here. Some crazy sort of materials science going on in order to get the metal powder into a polymer matrix that's able to maintain a shape while it gets sort of printed out.
We had a team of about 100 engineers and 15 PhDs, and we raised over $100 million from people like General Electric and BMW, Kleiner Perkins, etc., to build the company. But a lot of the material science that we've developed is standing on the shoulders of giants because there's 40 years of development in an industry called metal injection molding. And we use that chemistry and that supply chain so we don't have to have suppliers stand up capacity just to support us. We're able to take that type of metal powder that's being used to make all sorts of parts at much greater volumes than 3D printing today. And we leverage that low-cost material and then are able to then make parts with it using our process. We have innovated quite a bit on the process side, but we are standing on 40 years of standardization and research and capacity that's been put in place to support that industry.
And what parts right now are made using metal injection molding? Because I remember a couple of years back, there were all these rumors that Apple was going to start doing it, and I think that they metal injection molded the little SIM puller tool, but then as far as I know, they didn't really do any more with it. Like, what other kinds of things are metal injection molded?
So you're referring to something totally different, a different class of materials called metallic glasses, which are also injection molded. But metal injection molding technology is in every cell phone and in every laptop and in every car and in every medical device tool. It's how you make high complexity small parts. Billions of parts a year are made. Every time you have a flex connector inside a laptop, the little metal part at the end that attaches that or mates that to the rest of the chassis would be metal injection molded, or parts of your Apple Watch, or the lightning connector in those systems is metal injection molded. So we work with hundreds of alloys like stainless steels and carbon steels and titanium, etc. So it's a pretty robust, broad-based technology.
Do you need crazily different heating profiles for the sintering part of the process if you're using different materials?
Yeah, the way sintering works is you take the metal to about a little over 90% of its melting temperature, and then the diffusion takes care of it. And so you end up with a solid part at the end.
Oh, cool.
Yeah, so explain the difference between sintering and melting. This is a distinction that's important in the context you're describing it in, but isn't a distinction that people ordinarily encounter.
Yeah, they're different things. Melting is once you reach sort of the melt state of the material, and then you have a phase change and the material will become, in the case of metal, it would become liquid. And when you're sintering materials, it's a different process. Think of lots of different particles, and you put them together. And as you raise the temperature, once you go to the particles want to attract to each other, and the pores in between the particles close, and the part consolidates together until it's at full density. So it's a different process to densify materials. In vehicles, there's something called powder metallurgy. It's an industry where it's how you make gears in transmissions, and it's how you make all sorts of parts where you press material together and then you'll sinter it in the furnace, and then you'll get a fully solid part on the other end. And we're doing a similar process to that, but instead of pressing the powder together, we are creating a compact of powder and polymer in its proper shape together with the supports. We have a proprietary technology that allows you to separate yourself from the supports, where we print a ceramic layer between the supports and the part. So all of that goes together into the microwave enhanced sintering system, and that'll enable the part to consolidate isotropically.
Nice. So how do the mechanical properties of something that's sintered compare to, something that's like cast or...
Well, in many cases it's better, and it really depends on you'll have less porosity and other benefits. Using metal injection molding powder, because the particles are so fine, you're able to get fully dense parts or highly dense parts with better mechanical properties, and that technology has been advanced over, a couple decades. So we get excellent yield strength and tensile strength and hardness, all the properties. There's something called the MPIF, Metal Powder International Federation, which sort of sets standards for the materials, and our products meet all the MPIF standards, or the parts made with our systems. And so people that are in volume mass production are very familiar with what I'm talking about. So I don't know about your listeners, but people that are in a car maker or a place like Apple, or they do powder metallurgy all day long.
Just out of curiosity, what happens to the polymer matrix that the metal is suspended in? Does it melt and kind of run out of the furnace, or is it still in the material?
Part of the process dissolves it. It's in a multi-stage process. So you first dissolve the first set polymer, which is called a fugitive, and that will create porosity for the backbone, which is a polymer that melts at higher temperature that holds the part together until you form necks in between the metals. And so it's highly engineered. There's a whole range of additives that you put in to prevent cracking and other types of potential failure modes. And so this is a very highly engineered field with a lot of trade secrets and a lot of technology. And that's where a lot of the material science that we have comes in. Successful parts mean a successful chemistry. to start with.
So you just described a way of sort of designing it with a particular support structure so that the polymer dissolves properly. What are the kind of design constraints that users will encounter when they're using metal 3D printing that they might not be used to when they're using plastic 3D printing methods?
Sure. I mean, there's all sorts of design constraints, just like every other method. Like in the early days in injection molding, eventually people developed guides how to make injection molding successful. So there are ways to do this right, ways to do this wrong, and our software takes into account that, and we'll do proper orientation and layout of your part and build up supports to make sure that the part print is successful and that those also work through the sintering cycle. That's where a lot of the technology and art lies. There are things like mold lock. I don't know if you're familiar with that term, but you got to make sure your supports don't lock themselves into the part. You have to design it so the supports are easy to remove. One of the unique technologies that we have developed is something we call separable supports, which means that for the first time in history, you're able to remove supports on a metal part by hand. Our supports can be removed by hand. That just didn't exist before.
So that's the ceramic layer that you mentioned earlier that makes them breakable. How do you print ceramic? Is it the same process essentially?
Same process, yeah. You have a polymer base, a polymer matrix, and ceramic particles, and those are printed over the metal layer that you want to separate. The polymer dissolves, and then you end up with just sand, basically, between the two metal parts. It's super easy to use, super easy to develop, so it's a good technology.
Wow, that's really cool. I'm fascinated by ceramic now. I visited in Japan a few weeks ago. I was there with my wife on vacation and really wanted to take an industrial tour of a plant of some sort while we were there, and wound up going to the Kyocera Industrial Ceramics headquarters in Kyoto, where they have this giant...
Is that where the knives come from?
Yeah, that is. But they also do a lot of PCB-related ceramics and kind of like MEMS device type stuff, as well as like industrial abrasives and cutting tools and so on. And you have never appreciated the diversity and usefulness of industrial ceramic until you've visited a giant Japanese corporate museum dedicated to it.
So my partner in this venture, I have 4 MIT professors that co-founded the company with me, as well as a very well-known software guy that came out of SolidWorks, and somebody that I used to work with. And one of the professors from MIT is a fellow named Yat-Ming Chang, who is in course 3 in material science, and he is the Kyocera professor of ceramics at MIT. So he's a world-class expert in ceramics, and he developed this interface layer technology, or helped develop it, as well as helped develop the system so that our furnaces can operate in an office with none of the venting and permitting and all the crap that goes on when you're trying to get a conventional laser-based metal printer built or installed. And everything we've been telling you is about our studio system. We have the second product, which is our production system. What makes our production system exciting is that it's 100 times faster than the laser powder bed system that I was just telling you about earlier.
Wow.
Which is the current technology. So we have 2 products. One that for the first time lets you print metal parts in an office. It fits in a desktop. The second one, which is 100 times faster than a laser powder bed fusion. And one thing we didn't talk about, which is the fact that these metal injection molding powders are 80% cheaper than the powder used by laser powder bed. As a result, you end up with parts that are 1/20th the cost. So when you add 100 times faster and 80% cheaper raw materials, the parts are 1/20th the cost. So we have a process to print metal parts that is finally cost effective. And that's how we see the industry growing from $1 billion that it is today to the 80 billion that it'll be when it tries to match machining, or the 260 billion when it starts to take a bite out of casting and other techniques. That production system that I just described, our second product, it's cost effective in complex parts. It's cost effective versus casting up to 100,000 units. That's a big deal.
Wow. Up to 100,000 units?
Like continuously, like starting from 1 all the way to 100,000?
In our website on the production side, you can see a chart that shows that, and you can see a video that describes how that process works.
Wow.
Nice.
So that's the sort of the genesis of the company. Both of these systems use the same technique. We split the sintering from the printing. Unlike powder bed fusion, the old technology, which tried to do it all at once and then ended up with nothing, or with something that's too expensive.
Yeah, and also the printer's out of commission while the whole thing cools down too, right?
Yeah, and then it's super slow and all sorts of other constraints. Whereas if you can print cold, you can print fast. And then when you consolidate it, you have no stress. Everything consolidates at once, as opposed to having to build in stress. Because when you print layer by layer and consolidate with a laser layer by layer, the material is shrinking 8% in the case of aluminum, for example.
Oh, wow.
8% every 100 microns or every 50 microns. Imagine all the stresses that build up on that part. And as a result, we have a more mature, more exciting way to do it where you don't end up with stresses in the part.
Right. Could you give us kind of a general idea? And I know it's not possible without, knowing something about the parameters, but say you're thinking of an ordinary sort of sized chess piece that, like the castle piece that a lot of people use to demonstrate 3D printing results. How long would it take to go through the printing step and then the sintering step for a piece of that size that I'm thinking like 2 centimeters high?
Our production system is 500 cubic inches per hour. So assume that rook is a cubic inch. It's like 500 of those in an hour.
So it's almost instantaneous.
Well, it takes an hour and then you get all 500 at the same time. But you have 0 for the first 60 minutes.
Think about it this way. You have 14 inches by 14 inches by 14 inches.
Mm-hmm.
And that is in roughly 5.5 hours.
Okay.
So as many as you can pack in that build envelope, you'll get that in 5.5 hours. The desktop system is slower. It's a vector-based process. It's like FDM. And that's roughly 1 cubic inch per hour. So it take you an hour to print one of the rooks on the desktop system, on the studio system, and then you sinter it overnight.
So it's generally an overnight process for the sintering. For the industrial machine, so the desktop machine is similar to FDM. How does the substrate get laid down in the industrial machine?
The industrial machine is a process we call single pass jetting, and it works by basically having 2 powder spreaders that move bidirectionally in 2 directions. And so you spread powder in one direction, and you have full page width print bars. You have 2 of them. The first print bar lays down a binder. The second print bar lays down the ceramic so that you have interfaces for supports. And then you move in the opposite direction. So you move one direction, print and spread powder. Second direction, spread powder and print. So you're doing both, just moving back and forth, nonstop. Every slightly more than a second, every second and a half or so, you're doing 50 microns.
Okay.
Here's a question. How workable are the green parts before you center them? Can you test fit a bolt or a shaft or something into it and sand it down a little bit or something?
Yeah, this is one of the more exciting parts of the process, is that this allows you to work with ultra hard alloys like Inconel, for example, or Covars or Invars, or very high performance metallurgy. But when it's in the green state, it feels like clay. So you can totally machine it.
Oh,
it's
cool.
still strong enough that you're not going to break it into little pieces, but you can work it. And so you could do some of your finishing pre-sintering.
You can also iterate if you didn't get the design quite right, because it only takes an hour to print that little rook off again, and you don't have to go through the whole sintering process and everything.
You can do 3D nesting. So in powder bed fusion, you're stuck to the build plate. Here, you're not stuck to the build plate. You can literally nest the entire box. And also, you could start your print, and you're in it for an hour, and you didn't fill up the full bed, but now you want to keep throwing things into your bed. You can just throw models at it, and it'll stack them on top. So after you start your print, you can add things to it.
So another challenge that I understand people encounter in selective laser sintering, the SLS processes, is that it's difficult to use metals that are highly conductive because it kind of makes it hard to sinter only, the area that you're trying to sinter as opposed to sort of adjacent areas.
No, we don't have that problem. So people have been able to print things like copper in DMLS or powder bed fusion, which is kind of the old technology. But to do that, they have to totally slow it down. It is very hard and complex and very slow because of the nature of the conductivity of the material. So in our process, you could print any of these materials regardless of their conductivity. So copper is one of the materials that we successfully print.
That's incredible. So David and I like to get sort of philosophical when we talk with people who have cool new inventions. What do you identify as the sort of critical enablers of your new line of printers? Is it, for a lot of people, it's all of these mobile phone electronics are now available at unprecedented prices and performances. In this case, it seems like you're, as you said, standing on the shoulders of a lot of advances in metallurgy and materials. How would you characterize kind of the lead up, the timeline that is allowing you to do what you're doing?
Well, like all areas, Ellie Sachs, for example, is the inventor of binder jetting and is one of our co-founders. We are standing on, like you're saying, on the shoulders of 25 years, 30 years of work in that field. He graduated 200 theses that went through his group. So a significant amount of research. So a lot of the things that we're doing are basically a holistic view of how you turn this into a mass production, high volume process versus a sort of demonstration system. And that, which is what many of the existing prototyping systems have been to date. They've been kind of like demonstration systems to print one part, to do prototyping. Mm-hmm. They're not like super high volume mass production systems. And so for our production system, we took a holistic holistic view. How can we take a clean sheet design and go for productivity? And that's the goal of our production system.
What are the main challenges that you need to overcome in order to get people to adopt this stuff? Is there a learning curve that you're thinking about? Or
it's like everything, there's new process and new, but it's not so new that they haven't seen it before. It's basically a new twist on how to have a much more productive, lower cost system. I think proof is in the pudding. At the end of the day, people want the product we've got. We've got quite a bit of demand, and I think we'll end up with significant revenue this year in our first year of shipping machines. And, far more than I expected initially. So we're quite happy with the results of our launch, and the demand from customers has been overwhelming. We also have distribution now as part of a deal with Stratasys. So we had 35 VARs plus this group of VARs from Stratasys, which gives us basically the ability to get product out to market in almost over 100 countries. And we got now the ability to show the world what our stuff can do. It's not that hard to sell a product that's 1/10 the cost, and all of a sudden makes it accessible. There was pent-up demand for this.
Yeah.
So we have on the office side a product that's 1/10 the cost and is office friendly, whereas before they had to build a room around it and all these facilities. All our products fit through a door, and all you need is power. You don't need any special permits. The media is safe to use. And then on the production system, so that's the studio system I was describing. The production system, which is a product that will ship next year, demand has also been better than we expected. And it's because it's 100 times faster and the parts are 1/20 the cost. So we're sort of giving people what they want.
Fundamental economics. The ease of use is also something that has struck me. I visited a few companies that have conventional 3D metal printers and never use them because, as you mentioned, it not only requires extraordinarily expensive machinery, but also expertise.
Yeah, we look up to Formlabs in many ways. They've been very successful, and one of the areas where they're best in class is ease of use. And so we strive for our products to be very easy to use. We put a lot of time into user experience and usability, and basically the journey that a user has to go through to basically operate a machine. If it's too hard and it's not successful enough every time, people don't want to use the machine. And so one of the things that's unique about our system, you can change materials in less than 60 seconds. It's totally clean. That's unheard of in the world of powder bed fusion. If you think that SLA is complex to change a material, in powder bed fusion, they're down for a week.
You have to clean out the whole, you have to clean the whole thing out, right?
Yeah, with like a $7,000 vacuum cleaner and a spacesuit. I mean, you wear like a hazmat suit for a week. These factories don't have air conditioning. I mean, it's not pleasant.
You sound like someone who's been in a hazmat suit.
It's not pleasant. Whereas with our system, 60 seconds. And you can print materials that no other printer can print. You can print covars and invars and high conductivity copper and 4140 chromoly and all sorts of metals that had been untouchable due to the constraints of laser powder bed fusion. So that's one of the things that makes it really exciting. We have a lot of customers that are excited about being able to work with the alloys that they're using today for mass production, as opposed to having to constrain themselves to a small number of things that they can use in prototyping. One of the more exciting things is that you can prototype with the same materials that you'd use for production. Right now, they're using materials for production in castings and in forgings and other processes that literally are not available in laser powder bed fusion. But these materials are available in our studio system, and they're available in our production system. And that's a big deal.
So it simplifies the whole process if you're an engineer and you're trying to prototype with the material that you'll eventually use even through a different process.
That's right. And you can change materials fast. And it's easy to use. All you need is power. It fits through a door. You want to move the machine to another location. You don't have to call a facilities company. You don't have to build rooms around machines. It's super easy to use.
Does it use 3-phase power or 2-phase power?
It's 110 volts for the studio system for the printer, and it's 208 3-phase for the sintering system.
That's what you would want in those environments.
Right. I aspire to own a 3-phase 208-volt oven, but not available in my building. Ric, it's been a pleasure to speak with you. If listeners want to find you, where should they look?
Desktopmetal.com, and that's metal as singular. I don't know why some people say desktop metals.
All the metals you can print.
But you can do all the metals.
Exactly. So we're at desktopmetal.com, and they can also email me at ricfulop.com. That's Ric without a K at desktopmetal.com. And would love to hear from any potential customers or people that are excited about what we're doing.
Excellent. Thanks so much, Ric. This is the Digital Factory Podcast. I'm John Bruner.
I'm David Cranor.